A very good morning to my FYP supervisor, Prof. Thomas, my FYP coordinator and examiners. My name is Foo Ying Ying, metric number 178813. Here I am going to present about my FYP presentation. Title is Simulation and Optimization of Heat Pump for the Usage of Swimming Pool. This is a project associated with an industrial company. First of all, please allow me to introduce about heat pump. Heat pump is a system reverse to refrigeration cycle. Heat pump can recover energy by integration, which is recycle back the waste and environmental heat into the process. It has the potential to reduce greenhouse gases by replacing fuel as a heat generator. It is widely used not only in warming houses and swimming pool, but also in drying industry to dry the timber and food. There are four components in the heat pump system. As you can see in figure 2, they are evaporator, compressor, condenser, and expansion valve. The system is operated by extracting the heat from the ambient air by refrigerant R410 air in the evaporator. As the heat transfer has occurred between the fluids due to the temperature difference, then the refrigerant R410 air carry the thermal energy and transfer it to the swimming pool water in the condenser. This project is using fin evaporator due to its higher surface area for higher heat transfer rate. Therefore, it has higher efficiency compared to other evaporators. Besides, helical coil heat exchanger is used as the condenser in the heat pump system. The coil material used is titanium, which can resist the corrosion due to the swimming pool water contain the chlorine that will corrode the metal. Furthermore, I would like to introduce about the coefficient of performance COP in the heat pump system. COP is an important criteria in the heat pump system. It is a result of indicating efficiency of heat pump system or refrigeration system. COP can be defined as the ratio of thermal energy that being transferred to the pool water by condenser in the heat pump system and the work done by the heat pump, as shown in equation 1. It also can be defined as equation 2, where QH is the thermal energy transfer in the condenser, while QL is the thermal energy transfer in the evaporator. There are two problem statements in this project. First, heat pump of the company has low COP compared to his competitor. Second, it is hard to tackle the changes and ways that can be made to improve the COP of the heat pump by using the manual calculation. Besides, there are two main objectives in this project. First is to establish a model used to simulate the effect of changes made in the heat pump system. Second is to improve the COP of the heat pump with minor changes in the component. In addition, the 6 scopes of study in this project are shown as below. First, study about air to water heat pump. Second, identify the ideal software to create the model. Third, analyze the relationship between 4 components in the heat pump system. Fourth, analyze the design of the 4 components related to COP of heat pump. Fifth, study the effect of changes made in the model. Sixth, improve COP with minor changes in the system. Next, let us move on to the literature review. First, I would like to talk about heat transfer in the evaporators from my findings through the journals. Evaporator design in this project is fin and tube heat exchanger, which you can see in figure 5. There are 3 types of fin configuration, which are straight fin, circular fin, and continuous flat fin. Based on the journal by Wang, Xia, and Lin, 1997, the overall heat transfer coefficient is depending on the enthalpy potential, which is written in equation 3. Q average is indicated as the thermal energy, U naught is the overall heat transfer coefficient, N naught is the total surface area, F is the correction factor, and delta IM is the mean enthalpy potential. The overall heat transfer coefficient can be calculated by using equation 4 referred to the journal. As you can see, they are separating into 3 parts on the right hand side of the equation 4. The first part is indicating the properties of the fluid and the surface area on the inner side of the tube. The second part is actually indicating the properties of the metal of the tube, and the last part is the properties of the fluid flowing outside the tube and the surface area outside part of the tube. The heat transfer coefficient outside the tube can be calculated as shown in equation 5, and the heat transfer coefficient inside the tube can be calculated by using equation 6 based on Juniski 1976. Next, I would like to talk about heat transfer in the condenser. The type of condenser used is the helical coil heat exchanger. They are widely used due to their high surface area per unit volume based on Momale, Yadev, Pende, and Bros 2017. Figure 6 has shown the helical coil heat exchanger by Patel, Shandy, and Goss 1982. The heat transfer coefficient in the condenser can be calculated by using two equations depending on their Reynolds number. If the Reynolds number is around 50 to 10,000, equation 7 is used, while if greater than 10,000, then you should use equation 8 as shown below. The overall heat transfer coefficient of the condenser can be calculated by using equation 9, which is same concept as the evaporator part. So we have come to the last part of the literature review. Table 1 has shown the summary of energy performance of different heat pump systems. From the findings of Chow 2010, the achievable mean COP for the solar axis heat pump system is 6.46. From Park and Jong 2009, they have improved COP about 6% with the new refrigerant mixture. With Chai Wong Sa and Wong Wei Si 2008, their COP is approaching 6 by using the heat pump with the injector. Moreover, we are moving to the methodology of this project. The overall project methodology flowchart can be seen in figure 7 below. First, we have visit company for the discussion about this project. Second, we have analyzed the whole heat pump system to identify the problem and company requirement and the boundary of this project. The primary idea is generated by brainstorming, study, and discussion to get the overall picture of this project. After getting the primary idea, the next step is selection of the software. Based on Table 2, Microsoft Excel is outstanding and ideal to be used in this project. It is affordable, user-friendly, easy to access, has connection between software, and easier to understand compared to other software. After selecting a software, we have to determine the relationship between each component in the heat pump system. Then we have to identify the desired inputs and outputs of the model before we creating the model. And this is the last part of the methodology, which is modeling of the heat pump system. As you can see in figure 8, they are separating into three parts, which are input, system, and the outputs. After you key in the inputs into the system will automatically calculate the properties of the fluid, design, surface area, overall heat transfer coefficient, total surface area, and thermal energy of each component in the system by using the equation that have been set in the system. And the desired output of the system is the COP of the heat pump, can be get from the system after the calculation as well. Furthermore, we are moving to the result and discussion. First, the heat pump system in the Microsoft Excel will be shown. Figure 9 is showing the inputs that has to be keyed into the heat pump system that I have been mentioned in the previous slide. After keying the inputs, we are moving to the evaporator part in the system. Figure 10 has shown the heat transfer flow direction in the evaporator from the ambient air to the refrigerant R410A. After keying the inputs, the overall heat transfer coefficient of the evaporator can be calculated by using the equation as shown in figure 11. And the overall heat transfer coefficient get from the system will link to the thermal energy part in the system. From figure 12, we can see that The overall heat transfer coefficient is linking to the thermal energy transfer in the evaporator in this part, so that the thermal energy transfer in evaporator can be calculated as shown as above. After the evaporator part, the system will automatically link to the compressor part, which is the second component in the heat pump system. Figure 13 has shown the details of the work energy and the properties in the compressor part. After the compressor part, the system will link to the condenser part, which is the third component in the heat pump system. Figure 14 has shown the heat transfer flow direction from the refrigerant R410 air to the swimming pool water in the condenser. And the overall heat transfer coefficient of the condenser is calculated by using the equations shown in the figure 15. Afterward, the overall heat transfer of condenser is linking to the calculation of thermal energy in the condenser. And figure 16 has shown the thermal energy transfer calculation in the condenser part. Afterwards, the system will link to the part of the expansion valve. Figure 17 has shown the details about the expansion valve. And lastly, the system is linking to the final part of the model, which is the desired output of the heat pump system. COP can be calculated by using the equation 2, which set into the system, so that the COP can be calculated accurately by the system, as shown in figure 18. In addition, I would like to present about the effect of laminar or turbulent flow of the fluid. Laminar or turbulent flow of the fluid is important due to its relationship with heat transfer rate. Reynolds number is a determinant for the fluid flow pattern in the different situation. For Reynolds number, if the value for the flowing fluid in a condition is low, means it is in laminar state, while if the value is high, means it is in turbulent state. The equation of the Reynolds number can be shown in equation 10 below. Prandtl number is the ratio of momentum diffusivity to the thermal diffusivity. For Prandtl number, the smaller the value, which is smaller than 1, means the thermal diffusivity dominates, while the higher the value, which is more than 1, means the momentum diffusivity dominates the behavior. The Prandtl number equation can be shown in equation 11. The laminar flow or turbulent flow of refrigerant inside the tube can be determined by the Reynolds number and the Prandtl number that is included in the heat transfer coefficient inside the tube. The Reynolds number and the Prandtl number are included in the heat transfer coefficient inside the tube for the evaporator as shown in equation 12. However, for the condenser part, the Reynolds number and the Prandtl number are encountered in both in the inner side of the tube and the outer side of the tube. For the inner side of the tube, you can see in equation 13. For the heat transfer coefficient outside the tube in the condenser can be shown in equation 14, and you can see the Reynolds number and the Prandtl number are encountered in the equation 14. In order to create the turbulent flow in the condenser, the swirling effect is aiding in the condenser by creating an angle in the inlet for the swimming pool water to get into the condenser. The equation for inserting the swirling effect in the condenser are equation 15 and equation 16, which are shown as below. Table 3 is showing the result with and without swirling effect. Based on table 3, with swirling effect, the value for heat transfer coefficient outside the tube, overall heat transfer coefficient, and the thermal energy transfer in the condenser are higher than the one without swirling effect. Thermal energy transfer in the condenser with swirling effect is 7% higher than the one without swirling effect. Therefore, we can say that the swirling effect not only increases the heat transfer coefficient on the shell part of the condenser, but also improve the overall heat transfer coefficient as well as the thermal energy transfer in the condenser. And we have reached the last part of the result and discussion, which is the effect of changing surface area of the condenser. Table 4 has shown the total surface area of the tube in the condenser increasing, while the thermal energy transfer in the condenser decreasing with the COP value increasing. Figure 19 shows the graph of COP of heat pump versus the total surface area of tube in the condenser. As you can see from the graph, the total surface area of tube in the condenser increasing, the COP of the heat pump increasing as well. The total surface area is not only involved mainly in the equation 18, but also takes into account in the overall heat transfer coefficient to identify the flow pattern in that particular surface area. However, based on the figure 20, which is the graph of thermal energy transfer in the condenser versus the total surface area of the tube in the condenser, the thermal energy transfer in the condenser is lower when the total surface area of the tube is increasing. But when the thermal energy transfer in the condenser decreases, the COP of the heat pump increases. This is because the equation for the COP of the heat pump is made out by the thermal energy transfer in both condenser as well as the evaporator, which you can see in the equation 2 below. In this case, the thermal energy transfer in the evaporator is remain unchanged. COP of the heat pump is taking care of the overall efficiency of the heat pump. So, the difference between the thermal energy transfer in the condenser and the evaporator should be smaller in order for the COP to be higher. There are three conclusions that can be made from this project. First, Microsoft Excel is a better choice compared to other software in working on the basic of a model problem. It is good in terms of affordability, user-friendly, accessibility, connection between the software, and easier to understand. Second, the swirling effect that adding in the shell part of the condenser has enhanced the heat transfer coefficient outside the tube, and the overall heat transfer coefficient as well as the thermal energy that being transferred between the fluids in the condenser. Last but not least, the total surface area of the tube in the condenser also affects the thermal energy that being transferred between the fluid and the COP of the heat pump. The greater the total surface area of the tube in the condenser, the higher the COP of the heat pump. The COP of the heat pump can be improved and enhanced based on the recommendation below. First, increase the turbulent flow of the water by inserting the angle at the inlet of the water in the condenser to create the swirling effect for the water to flow into the condenser. Second, increase the total surface area of the tube for the thermal energy to be transferred from the refrigerant R410A to swimming pool water. Third, use the inverter inside the heat pump system to lower down the energy wastage and enhance the efficiency of the heat pump. Fourth, insert fan generate swirl to create the turbulent flow inside the condenser to enhance the heat transfer rate. So that's all from me, and thank you for listening to my presentation.